a chemist's perspective. So quantum computing is something we all know that it is evolving. So I'll be using the following outline: introduction, quantum chemistry and computational chemistry, quantum computing, and then fundamentals of quantum computing and the intersection of quantum computing and chemistry or computational chemistry. Then challenges in computational chemistry, which quantum computing is trying to solve through some researches. And then we have specific applications and case study and examples, and then conclusion. So I will not take your time at all. Quantum computing is a fast evolving field that promises to transform various various industries, including finance, cryptography, the health sector, and of course, education, then chemistry. We use computational chemistry, and the traditional computing, which is the classical computing or classical computers which we use in computing, has served well, allowing us to simulate and understand complex chemical processes to some extent. However, as we delve into more complex systems involving very large molecules or interactions at the quantum mechanical level, we encounter some limitations that challenge our existing computational methods. And so in this era of growing intricacy in chemical research, understanding and leveraging the potential of quantum computing could significantly enhance our ability to innovate and solve pressing problems. Quantum chemistry, we all know, is a branch of chemistry that uses quantum mechanics to explain and predict the properties and behavior of molecules, atoms, and their interactions. Quantum mechanics revolutionized our understanding of chemical systems by helping us see or showing us the fundamental principles governing what? Atomic and molecular interactions. Now, computational chemistry translates these quantum mechanical principles into powerful tools that simulate and predict molecular behavior with remarkable accuracy and details. When we say beautiful tools, we talk about the systems we use, the softwares we use in computational chemistry, such as the one from Schrödinger, which is we call Maestro, the one from wave function, which is pattern, the one from, we have FIMO, depending on what you want to do. We have softwares that we use for these things and under computational chemistry. So quantum mechanical methods anchored by the Schrödinger equation. You cannot talk about quantum mechanics without mentioning Schrödinger. Schrödinger equation is the bedrock of the calculations we do in computational chemistry. So Schrödinger equation, which forms the foundation upon which diverse applications in chemistry and material science flourishes, and even drug design. This is the basis, the fundamentals. So examples of quantum mechanical methods that we employ in computational chemistry or quantum chemistry is we have the semi-empirical method, we have the Hartree-Fock method, we have the density functional method, we have time-dependent density functional methods. So these methods, these are the methods we use with their basic sets that we use in calculation. Like for the density functional theory, we use Beck-3 and Parr basic set, which is more accurate than the Hartree-Fock and then the semi-empirical methods. And so I want to talk about quantum computing before I now merge the two together. I hope you will be able to watch this. It's just a 5 minutes video about quantum computing. It summarizes quantum computing.
No volume.
What about this?
This is mute, yes, I cannot hear you. Myself is, I can't see. Yes, it's mute.
Jesus. Part they are.
So okay. So that's quantum computing. A brief intro about quantum computing. So I'll ask you some questions. You audience, you answer. What's the similarity between quantum computers and classical computers? In computational chemistry, we use supercomputers and classical computers. So from what we just watched now, what are the similarities? Is there any similarity? Sorry. Can you hear me? Are they still on?
Yeah, I think. But I didn't want to connect us. You know, they're not sharing.
Okay, directly. Okay.
You are sharing online. So this online can hear you clearly.
Okay.
So if you are sharing that, we will be able to, but share version.
Okay.
Yeah, so okay. The only thing people here also participate. I guess another question is posed to us, we that are here, not necessarily those who go online. Okay, the similarity between the classical and quantum.
From what you watched, or you didn't watch it. Okay, some of the similarities, they have what? They have logic gates, circuits, and what else? Chips, yes, computer chips. And then they also have they operate by algorithms, but different algorithms. Then what are the differences? Yeah.
Differences is the bits.
Yes.
It has just a how many occupy one state at a time.
Yes.
So the qubits exist in the superposition of all the states from particular states. Then also the speed, the way the computational process is carried out. For classical computers, it goes through each query, each item one at a time. But with the quantum computing, it explores all parts until it collapses to particular part of the logic.
Yes, thank you. So those are the differences. Another one is that it solves problems faster as a result of the bits, the qubits that it uses. So quantum computing is a new paradigm of computing that leverages the principles of quantum mechanics, such as superposition and entanglement. You know, in the classical computers, we said the quantum methods, the quantum mechanical methods are DFT, semi-empirical, Hartree fork and co. But this one uses superposition and entanglement to work, to perform calculations that would be practical and for classical, that would be impractical, difficult for classical computers. For example, when I'm trying to calculate the energy of a system using classical computers, depending on the size of the molecule, is always very slow. Sometimes it could take days, it could take weeks, it could take months, depending on the size, and the computer gets tired easily, except you are using a supercomputer, which makes it a bit faster. But with the advent of quantum computing, these calculations can come, in fact, very fast, in a matter of seconds or even minutes for the large molecules. So the fundamentals are those superposition that we talked about, the qubit, using qubits instead of binary bits, the entanglement of the qubits, that's the connection. And then the connection, no matter the distance, one affects the other. They all affect one another. And we have a lot of them. So if you have, like in chemistry, if you have a molecule that has 250 molecules, now for the classical, it has to do correlate the electron density, calculate one after the other. But with this one, it could see the bits, this qubit that we are talking about, it could see it both in the two forms, that it can exist in both forms, and so makes it faster. If you have 250, the square root of 250 is the time it will use to calculate, or the number of calculations times it will calculate that molecule, which is very fast compared to classical computing. Then it has algorithm where it uses Shaw's algorithm for factorizing, and then Grover's algorithm for searching. So where in chemistry we are searching, we are making a conformational search. Maybe this molecule that is 250 molecular weight. It has a molecular weight of 250 grams per mole. And then we are looking at, it has maybe 250 molecules, like when you have the proteins that are very large in drug design. Now, it has to make what is called a conformational search. It will do it so as many times as possible. How many number of times it would have to check these things. With the advent of this computing, quantum computing, it will be very fast because of the Grover's algorithm that is embedded in it. So quantum computing interacts with chemistry primarily by providing new methods of solving complex problems that are integral to understanding molecular behavior, chemical reactions, and material properties. So traditionally, quantum mechanical methods, that's the Hartree-Fock, the density functional theory, struggle with complex systems, which I've mentioned before, especially for very large molecules and for materials. But there are limitations in accuracy also when computing this kind of large data set, and computational resources are not there. But with the advent of the quantum computing, this problem is solved, this challenge is solved because it performs quantum simulation naturally and efficiently, modeling electron interactions. And then it uses quantum states to capture electron correlation and excitation behavior directly and naturally, allowing for more accurate predictions of molecules' properties and then their reactions. So it is something we need. So some of the specific applications of quantum computing in chemistry could be the calculation of molecular energy. We do molecular energy calculations like the HOMO and the LUMO, highest occupied molecule. When you have a molecule, that molecule has a HOMO and a LUMO energy. That's highest occupied molecular orbital, and then the lowest occupied molecular orbital energies, which we do using either of the quantum computational methods we have mentioned. But for large data sets or large molecules, it's always very difficult. So this we can achieve using these algorithms that the quantum computing has. So it could make the conformational search easy and faster. What is conformational? You have to find, before you can do any calculation, you must bring down that molecule to a ground state, a stable state. So it has to do a lot of search on the molecule to find that ground state, that stable state. And that is, with this algorithm that it uses, it will be very easy to compute such energies. And then we have calculation and chemical reactions. We can look at transition state calculations or energies of a molecule, how a molecule reacts. So that transition state can be calculated too. It's something the quantum computing can do for us easily and fast. And then in material science, you have to bring a lot of things, a lot of molecules together to make a material. With the factorizing the Shor's algorithm and the Grover's algorithm, this makes it very easy to have this new compound or new materials synthesized or calculated and then brought out or designed. And when designed, then we can go to the lab to see what we can do. But that reduces our wastage of chemical and other things that we need in this area. So those are the specific applications of quantum computing in chemistry. I have not used one before, but I know. As I was reading through, I know people are using something, especially in the drug area, drug design. They are trying to do something, which we'll get to when we get to the case study. So this case study, we noticed I saw that IBM and University of California, Los Angeles, they are collaborating to focus on using quantum computers to do what? To simulate the binding affinities of drug candidates to their target proteins. And the research looks at how quantum computational methods can complement existing classical techniques in what? In predicting the interactions of small molecules with what? Protein targets. Because these protein targets are very large. They are large, and so these calculations will be done easily, and then the conformation searched and then gotten. Then we also have another case where Rigidity Computing and the University of California, Berkeley are collaborating on developing quantum algorithms for drug discovery applications. And this focus is on simulating chemical reactions. You know, I talked about chemical reactions, simulating chemical reactions relevant to drug metabolism. So how the drug is metabolized in the body and assisting in what? Predicting how modifications to drug structures can influence their pharmacokinetics and their pharmacodynamics. So quantum computing has come to stay. So leveraging the unique capacities or capabilities of this quantum computing, researchers can enhance their understanding of molecular interactions, streamline their candidates' identification, and tailor compounds with optimal properties. So instead of wasting chemical, trying this, trying that, you are sure of what you are doing. When you have done the calculation and it is correct, then you can go to the lab. You know exactly how many moles of this you will mix with that, and in what the conditions of the reaction to get what you want. And this, as far as quantum computing can go in chemistry. Thank you for listening. Any question?
So I'm using my camera. So thank you for the presentation. Do we have any questions from over here? Do we have any questions online? Do we have any questions from here?
I have a number of questions because I followed the lecture and was quite interesting. And I know that from 3 days ago, we started on Wednesday, some things keep coming up together. Now, those things that come up from the different areas of specialization are used differently. So, for example, I love to see a case where you talk about the methods. Those methods include, you mentioned the fork tree, the active fork tree, yes. Then you mentioned the DFT. We in mathematics, we use the Hilbert space. An example of a Hilbert space where these operations come up is the Fock space. In the Fock space, you have a couple of Hilbert space. So our tensor product has its own representation. Yeah, so I don't know if there is a kind of representation that we can see that describes the active fork tree or the active fork tree.
Active fork method.
Okay, active fork. Yeah. So it's a method. So I mean, I'm thinking. I mean, there should be a way it connects with what we do. That's one. Then I also see the DFT. I know the DFT is used very much in physics. Yes, they use it in theoretical physics. They are doing research. Even here in UI, I know of Dr. Wololu and some of the students that are actively using that. Now that, I mean, it's not coming to chemistry also using the same tool. Yeah, I love to see how, I mean, the electrons would have been combined and these activities are done using these methods. I don't know, but if you can give us references, that would be very good for us because it gives us a lot more exposure. Then also, the lady that spoke yesterday gave us some electron combination. She's not here, unfortunately. I don't know why she's not here. And I was telling her, well, I would love to see this being spoken by the professor that is going to give us a talk tomorrow. if she were here now, she would have been able to describe it more. Because like from what you have explained now, the fact that the quantum methods helps and makes work a lot faster and easier. I mean, it's a fact we have to hold. Good. If here we don't have a lab for such, in the labs that we know, can we have some of the experimental results that they have that shows some of this? Yeah, I don't know if there are references that would be good for us, so that the collaboration we are thinking of and training can be for everyone. I don't know. I think these are areas that we need to look at and see more of. I don't know if there are other comments and questions.
I personally have a question.
Okay.
So, from the physics perspective, quantum computing runs based on the principles of superposition, entanglement, the evolution postulates, and what's the name for the last one? So I wanted to ask, are there processes in chemistry that quantum computing also borrows from? Are there ideas in chemistry that quantum computing borrows from or could potentially borrow from as the field grows wider?
Even if you speak
From, this computing system is new here. It's new. So we have not really explored, experimented or explored. I don't even know a lab where, because what we used to do for the supercomputers, we normally send our data outside for the supercomputers, because especially if the molecule is big, is large, we have to send, but we don't have supercomputers here that run. So if you have a link, they give you a code, so you send it out and they run and return the results to us. So we now interpret the results. Why we do that is because this computer cannot do very large move. If I leave it on for a month, it's dangerous for the battery of the computer. Yes. So because the data, so that's why we use supercomputers if we have to do large moves. But for what it can borrow, from what I have seen, while studying the qubits, it's very nice when it comes to all this conform. I talked about conformational search. The number of times it will do the search, the calculation, before it gets to the one that we actually need for the other calculations. It takes time when the data set is large. So, but from what I saw as I was preparing here, it's like it makes it faster. It will make it faster, I assume. It should make it faster than what we are using the classical computers to do. So that's just what I feel it will borrow from chemistry. And I know there will be a lot of things once we start exploring the method, the computing method.
one question I think I want to ask, just for clarity, is when you talk about large molecules, in that case, how do you use the computer to check the confusions of that molecule? I don't know what. I know what you used to do is your H2O is hydrogen plus oxygen, balance chemical equation. Oh, you don't know that large molecules and the computer working on it for a long time. I just started imagining. Like in organic chemistry, there have to be, chains.
Yes.
So are you going to write it down and send it abroad, or is it? It's
No,
how?
So you have to draw the structure, give it and then send it. Because it's the structure with, like this pattern I have here. I have this pattern here. You draw a structure, you have to draw the structure before you start any, because it's on that structure it will do itself.
It's not quite sustainable for us.
Okay.
Yes, just share and come and help share. Because it's quite interesting to see the way these things are applied. And it makes it much more clearer and more beautiful for people to follow what we are saying and not like just mastering by in the abstract for like the mathematics. These are more reality. So,
Sorry. Let's like this. Okay, so which one do you want to show? I have the document.
So this is software.
please share it.
I want to let it open.
So you want to talk.
So I can I work on it inside while I'm sharing? Yes, 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 yes. I share. Why is this so stressful? How is going to? Okay. I think this thing is touching. Which one pass? No, it's not. It's one the last spoken. Okay, let's end that. So I want to have to build a molecule. Can I share this? No, I want to. Let's do that. Okay. I want to build a molecule. Just build. build. Okay, so this is two benzene rings fused together. Two benzene rings fused together. So I want to carry out calculation means. It's going to, if I use DFT, it's going to try to find the conformation that is good. And after that, it will do calculation on each electron in each of the atoms. So here, this is the molecule you have to minimize first. So I have to minimize the molecule. Yeah, okay. So now I will carry out a calculation, set up a calculation. You see this Hartree fork? I want to do DFT. Right, Hartree fork will be faster than me. Okay, let's even try it. Hartree fork. Let's do this Hartree fork. Let me do DFT straight away, then go to Hartree. So we use this basis set. And let's say in vacuum, you're not using solvent. If I want solvent, I'll change it to solvent. So in vacuum, then I want it to give me orbital calculation, and then think current geometry. And then I submit my feedback. So the calculation has started. Now you can view here, if you come to yes. So The calculation is already on. So, one, two. Please, can I plug the computer? The battery is low. Yes. Sir.
Just connect.
No, they have a head. Okay. Sorry. Yes, yeah.
So it's blocked, right?
Yes. Yes.
So it's like a software used
Yes. To do calculations.
to calculations or simulations on molecules.
Yes.
Wow. It's like we have Python, we have maybe language.
So we have this, we have Gaussian. This one, Gaussian is more elaborate than this. This one is easy to use, this pattern, easy to use, but Gaussian gives better calculations than it's better. So, especially when it comes to large ones. Maybe I should abort it and do benzene. Benzene will be fast because the molecules are in place. It says it has completed the work. It has completed. So let's see. I asked it to do the orbital calculation. The HOMO. And then let's see the electron density, electron potential. So if I click on any of this, you'll see that. I want to move this. Okay. So this is the compound. This is the HOMO energy. This is the highest of 5 molecular orbital energy. This, it has calculated, it will go to check the result. So we did this for the electrons. So here is showing us the orbitals that are giving out electrons to the system. That's the ones painted there. Then yes, red and green, yes. Here is the LUMO in the ones that are in the highest, lowest occupied molecular orbital during excitation. So this is the structure. And then when the electronic density or potential of the compound is showing us, okay, if there's no red here, there's nothing red here, that means we don't have electron density, a lot on that compound. Maybe it's on the I rings, and then we can check the output to what we have asked it to calculate. We can get our results from the display, the result, properties. So you can see it gave us the energy calculation. The lowest energy compound is what it used to do the calculation. Then this is the HOMO, the E-HOMO, the energy of the HOMO, highest occupied molecular orbital where the electrons are. Then we have the lowest occupied molecular orbital. Now, if we subtract this, the E-LUMO from the E-HOMO, we will get what is called band gap. There's a change in energy, HOMO-LUMO. And that will give us the result we get. We can interpret it in such that, is this compound reactive or not, or in terms of the reactivity of the compound. So with the HOMO, the LUMO, we can do business with so many calculations. We can use them for so many. Then it's telling us that the compound I drew has no dipole moments. Talk about dipole mobility. We talk about the group theory. It's a D2 in symmetry. It's a D2 compound. And with all this information, if you carry it out for so many compounds, you can do what? You can find out the quantity, the structural quantity activity relationship in terms of reactivity. So those are the things we do. And with that, we can use it to predict a lot of things in the industry. So that is this time. If you notice the time it took for this to be completed, if I do it for Hartree, it will be faster than that. Very faster than that. But this result is more accurate than the before. So depending on lecture. So we have other complex roots. So if I increase this compound now, maybe you have like 3-4 benzene compounds or very large protein compounds, the calculation will take a lot. Because it has to visit every atom one by one, take the electrons one by one. But for the quantum, for the quantum computing, it can recognize those atoms, take them at once. Yes, and do the calculation. That's the difference.
Since this is quite clearer than when you listen to the theory, like she gave you before. I mean, you see the picture of an electron and you see the question. You have a question? Okay, please. Yeah, come on.
Thanks so much, man. Yeah, thank you so much, sir. Thank you so much. While you were presenting maths, particular place, very important on like cloud as well. Comments on the fact that using quantum for proteins, you're talking about how it's being used for pharmaceutical aspect. And can you elaborate on me? Just I know it's got on just the way of sharing because I found that person not likes so we some computing on speed. It's not only meant for making nuclear or something, also see that application from the real okay, pharmaceuticals like infection here, quantum study of schools. You have done the same thing.
Yes,
Please.
Okay, okay. So in pharmaceutical chemistry or in drug design, you are looking at how you have a target. Is receptor and target oriented. You have which like you have, how do I describe it? You have a phase. What fits into this phase? Let's say there's a particular disease. We want to inhibit that disease. And inhibiting that disease means looking at the protein that the organism leverages on. And then we try to look for something that will fit, that will block its proliferation. So getting that thing that fits, we can do calculation to find out there's another software that we use. Yes, we call it docking. We have to dock the protein and the target. Maybe you have like ampicillin, that's a chemical. How you can dock it on the protein, maybe what the enzyme is for wounds, some kinds of wounds. So the wounds that you have, what is the enzyme on the protein or the organism? What does it have that is attacking it? Let's say like tetanus here. Tetanus is in that way. Now, what is in that bacteria that inhibits with this ampicillin that will fix? So those are some of the calculations you do. And then when we get it, we look at the docking score. Does it is docking score? If it's high, that means it can block its actions. Yes, it's good. And if it can do that, then we do what we call molecular dynamics. You check the stability. Can it, if you try to calculate if it is stable, the binding is stable. If it's stable, that means it can do the work. So you go ahead and produce that in, and then try to do clinical trials if it's happening. So that's the way it's the receptor targeted. So let's say like cancer, there are some compounds and the bacteria, the cells that the cancer cells, what is in that cell, what is causing this cancer to proliferate? Can we get a substance that can block that thing? So if you can get what fits and you check the dynamics that it's stable, then your rate of discovery is good. So that's why this continuous discussion. So when you have done it on the company and it works, it gives you a high value of docking score. And then it gives you a high value of the simulation. You get what is it called? And you use in mathematics. RMD, what's it? RMD. Root mean, yes, yeah. So if it gives you a good, then you can go ahead and synthesize that instead of wasting chemicals, trying to try here, try here. So that's the way we use these things in the trust.
Yeah, it's a good exposure because my first time of really seeing how this thing comes to play. This is if you see this amongst us, he's not listening. You had what she explained. When I told you where this, you can see now. She's from physiology department and she's a master student. So you can see it's a ball of collection of everybody coming together. I've learned so much because in those terms you use, I know in physics they use stability, some person like that. You must use the same thing. But when you talk about group, I was thinking, like because you use
synergy and mystery.
You use the physics. And you know one thing about the Fox space, you have this metric Fox space, you have the and that gives us the Bono Fox space and the Federal Fox. So this thing seems to be coming together. And we keep learning from ourselves. So I think we appreciate what you have done.
Thank you.
Thank you.
Okay, I've stopped sharing so I can hear. Okay.
All right. So give a round of applause to Dr. Lemon. So we'll be taking a 5-minute break before our next speaker, Mr. Kenneth, comes up. So stay tuned. We'll be back in 5 minutes. Thank you. All right, so we're back, and now we'll be calling on Mr. Kenneth to give his own talk. So, Mr. Kenneth, you have the floor.
Yes, speak.
Okay, hello everyone. Let me quickly share my screen. Okay, I don't know if my screen is visible. So is my screen visible? Okay, let me check the chat.
Yes, your screen is visible.
Okay, perfect. Thank you. Thank you. So hello everyone. I am Kenneth Samadi. I'm a software developer and I'm also a quantum computing educator. So I'm going to be taking you through the basics of quantum computing and Qiskit. And I'm also going to introduce you to variational quantum algorithms. Okay, so before I introduce quantum computing, I always like to start off by explaining what classical computing is. So classical computing is a mode of computing whereby the smallest piece of information is stored as a bit. And a bit is a two-state device, which can take on the value of 0 or 1. So what we're usually trying to accomplish with computers is that we want to be able to store information, we want to be able to change the values that we've stored, and at a later time, you might want to read out the stored values. So in a classical computer, this information, the smallest thing I can store is a bit, and it can take on the value of 0 or 1. So when I've stored my information and I want to make changes, I utilize gates. And these gates, they operate based on the laws of Boolean algebra. So you can create truth tables whereby you apply some logic gates and it will change your value from 0 to 1, 1 to 0, and stuff like that. So we combine a couple of gates in a circuit to accomplish more complicated tasks along the lines of arithmetic and logic. So something like addition, we're going to utilize a couple of gates. Okay, so this is all I've just been trying to describe. We're storing values as 0 or 1, and we have gates like the NOT and OR gates that we can use to change those values. Okay, so now we're moving on to quantum computing. And in quantum computing, we also have quantum computers, and they're supposed to work differently from classical computers. So the thing is that, okay, in a classical computer, I can store information, I can change it, and I can read out those values. So why do I need a different type of computer? So that's what I'm going to explain in quantum computing now. So quantum computing is actually a multidisciplinary field. It comprises of aspects from computer science, physics, maths, chemistry, various fields. So in a quantum computer, I'm also storing information, but I'm not storing it as a bit, I'm storing it as a qubit. So a qubit is the smallest form of information I can store in a quantum computer. So how is it different from a classical bit? Because our qubits are also physically realized using two-state systems. So we're going to see how qubits are different, and we're also going to apply gates to change the values stored in our qubits. Okay. So what makes a quantum computer different from a classical computer is that there are a couple of properties that there are a couple of properties unique to quantum systems that we're going to try to utilize in our quantum computer to get some advantage over classical computers for certain tasks. So the first is superposition. And for superposition, what we're trying to do is that what we're trying to do in superposition is that we could have a situation whereby we could store 0 or we could store 1, but we could also have a situation whereby we're storing both 1 and 0 simultaneously. That's not exactly the case, but I think that is the easiest way to get it across at this point in time. So we can store 0, we can store 1, and we can store both 1 and 0, but both 1 and 0 in a single qubit at the same time. We also have interference. So we also have entanglement. And entanglement is a situation whereby we have multiple qubits and they are correlated in such a way that even though they are far apart, even though they are far apart, they are still strongly correlated. And finally, we have interference. So interference is not necessarily a property unique to quantum systems. Interference actually started off with waves when we were exploring waves classically. And it's a situation whereby a couple of waves can interact and they interfere. A couple of waves interact and they either cancel themselves out or they reinforce themselves. So the thing is that in quantum systems, or okay, not necessarily quantum systems, naturally, particles or objects have a wave-particle duality. So they can behave both as waves and particles. But in classical systems, they are too large. So it's hard to see the effects of, it's hard to see the wave-like properties in these classical systems because they are too large. But in quantum systems that are really small, these wave-like properties become more apparent, and because of that, we can see properties like interference. Okay. Okay, so still on entanglements, we just have qubits that are correlated. And even if I was to place these qubits at opposite ends of the universe, they will still be correlated such that if I was to check one, or if I was to read information from one qubit, I will instantaneously have information about another qubit. Okay, so this is what I was trying to describe in terms of superposition. So in superposition, we actually have a linear combination of 0 and 1, such that there is some probability that I have 1 stored in my qubits and some probability that I have 0 stored in my qubits. So if I had a qubit and the value, if I had a qubit and it was in superposition, there are sometimes if I checked, I could see a 0, and other times when I check, I'll see a 1. So in this linear combination, the coefficients are complex numbers. So we also have quantum gates. Here are a couple of quantum gates that could be applied to change the values that we've stored in our quantum circuit. So we can store values, we can apply gates to change them, and at a later point in time, we can read those values, and that's where measurement comes into place. So even though in our qubits we can have superposition, whereby there's some probability that 0 is stored there and 1 is stored there, we can't directly check to see this superposition. We can't check to see that, okay, there is a 0.2% chance that my qubit is 0 and a 0.8% chance that my qubit is 1. We can't directly check to see this linear combination. So during measurements, we just observe the qubits, and when we observe it, we see either a 0 or 1. So we have to like repeatedly carry out measurements to get some probability distribution, to have information on what the superposition was like. Okay, so this is so our qubits, when we want to represent what's stored in our qubits, we can utilize vectors, and that's what we're doing here. So if I have a single qubit, I can have a two-dimensional vector to represent what's stored there. If I have 2 qubits, I can have a 4-dimensional vector. So the first entry contains information regarding if, when measured, I'll see 0, 0. The second entry 0, 1, and like that up until the end. And if I had a quantum state with 3 qubits, I'll have an 8-dimensional vector. Okay, so I think someone wants to ask a question. You can unmute and ask.
Yes, thank you, Mr. Kenneth. The first question is about the chances of the two states occurring at the same time during entanglement. Can it be of equal chance? Because you mentioned the probability of two states occurring at the same time. Sorry, during superposition. Yeah, so is it possible that it's an equal chance for the two states to occur at the same time? Then I guess also for the 3 qubit states, the 8 values will be a combination of zeros and 1, all true. Okay.
Okay.
So it will be like a permutation or a rearrangement of what we have that we are seeing on the screen. Yes, thank you.
Okay. So thank you for that question. So the first concerning if it's possible to have an equal probability of getting 0 and 1 in superposition, yes. If in a system with a single qubit, if the amplitudes are equal, that would mean there's an equal chance of getting 0 and getting a 1. So here I have 4 different states, and if they were all equal, if all these values were equal, there's an equal chance I get 0, 0, 0, 1, 1, 0, and 1, 1. And so when I was speaking about the vectors, so I said in a single state system, in a single qubit system, I can use a vector of 2 dimensions to represent the states. Each of those entries, the first one would be the first one would have information concerning the probability of it ending up with 0 when I measure, and the second entry will contain information about me seeing 1 when I was to measure. So in a 2-qubit system, all the different states you see here, this will be for 0, 0, 0, 1, 1, 0, and 1, 1. So yeah, so we're going to run a combination of different possible ways that I could utilize zeros and ones. Depending, so like, because I have 2 qubits, I just have 2 values here, and we're going to run a combination of all the different possible ways. So here in the 3-qubit system, as you can see, I started off with 0, 0, 0, and I ended up with 1, 1, 1. So I have all the different possible combinations. That is 0, 0, 1, 0, 1, 0, 1, 0, all the different combinations are there. And the probability information would be, I don't know if that answers the question.
Yes, thank you.
So do we have any questions here? Or online?
Okay, so it doesn't seem there are questions, so I'll proceed. So these are a couple of ways to implement our qubits. We can use trapped ions, superconducting circuits. Companies like Microsoft are working with topological qubits. So you can use photonics. There are several ways we can implement our quantum circuits. Okay, so our quantum circuits are prone to error. So we need to like incorporate like really advanced engineering methods to shield our circuit from external noise. So we could do things like cooling it to really low temperatures, shielding it from magnetic fields and vibrations and stuff like that. So there are several places we might want to utilize quantum computers. Examples include chemistry, material science, machine learning, optimization problems, and those are like the current problems that we're trying to tackle with quantum computers. So currently we're in the NISQ era, and right now our quantum computers have few qubits and they are really prone to error. And hopefully in a couple of years we get to fault tolerant quantum computers whereby we've incorporated error correction and the values we get are reliable. To speak, this is just still on possible applications. So in like chemistry, we could use it for DNA binding, protein folding, battery design, drug design, stuff like that. In machine learning, there are algorithms for reinforcement learning, generative adversarial networks, stuff like that. We could also use it for optimization to optimize routes and schedules and stuff like that. Okay. So I think that provides a good introduction to quantum computing. I think I'm going to show a bit of what a quantum circuit is like. So here I'm using Qiskit to implement a quantum circuit. So Qiskit is just a library. It's a Python library. So I have Python installed, and I can also install the Qiskit library. And it's provide me with a couple of functions and methods I could use to design and read values from my quantum circuits. So here I have a quantum register, and this is where my qubits are in a quantum register. So I can request for a certain number of qubits. In this case, I'm requesting for 2. I could also have a classical register. So here I have bits, not qubits. And here I'm requesting for just 2 bits. And I have my quantum circuits. So it's in my quantum circuit, I'm going to apply gates to change the values I have in my quantum register. So that's what's happening here. So I have my quantum register, my classical register, and I have my circuit where I've introduced the quantum and classical registers. And finally, I can apply gates. So these are a couple of gates that are being applied to my qubits. And then finally, I can measure and get results. So when I perform measurements, as you can see here, I'm providing both my quantum and classical registers. And that's because I want to store the values I read. Because when we measure a qubit, we're just going to end up with some classical results. So we're going to store it in our classical register. So this is a quantum circuit. These are a couple of gates. So these are gates that we can apply to single qubits. And this is a multi-qubit gate. So you can't just apply this to a single qubit. You need to specify 2 qubits. So this specific gate, it's called a CNOT gate, and it works such that depending on the value of 1 qubit, which we call the controller, we can decide if we're going to change a different value, which is what we call the target. So this is a 2 qubit gate. And we utilize this to create entanglements. So this is how we actually create those correlations. Okay, so I can specify where I want my quantum circuit to run. So here I'm using a simulator. I'm just using a simulator running on my local classical machine, because we can actually utilize classical computers to do what we are trying to do with quantum computers. So a classical computer can perform the same tasks as a quantum computer, but the catch here is that we can only do this depending on the number of qubits. So my local device now, I don't think I can even go up to 30 qubits. Beyond that point, the computation just becomes too complex for my computer to handle. And even for really powerful supercomputers, when we get up to maybe 50 qubits, it becomes too difficult for those supercomputers to run our quantum circuits. So this is why we need quantum computers. So when I've specified where I want my circuit to run, I can run it and retrieve results. So in this case, after running my circuit, I was able to get, so this is the probability that I get 1. So let's say okay, so here, I was able to run my circuit 1,000 times. And when I was checking the results for a single qubit, 513 times, I got 1. Sorry, 513 times. Okay, I had 2 qubits, sorry. I had 2 qubits. And 513 times, I got 0, 1. And 487 times, I got 1, 0. So we're just retrieving classical results from what we did in our quantum circuits. So this is just the process. So I was just trying out different ways to retrieve the results. That's all that's happening here. Okay, so still more on quantum circuits. So I spoke earlier about the state of the state of our qubits being stored, or using a qubit, using vectors to represent the states stored in our qubits. And I can actually retrieve those vectors. So here, I'm utilizing a state vector to see what the entries in our vector is. And as I said briefly earlier, the entries in our vectors are complex numbers. So as you can see here, we have complex numbers. And also our operators that change these values can be represented as matrices. So here, extracting the matrix that was applied in our quantum circuit. Okay, so this is called the block sphere, and it's just a sphere that we can use to represent the state stored in a single qubit. So we have an arrow here, and anywhere we point this arrow such that it touches the sphere, it's a possible value that can be stored in a single qubit. So currently, you can see where the arrow is going and touching the sphere at that point. So that's currently the state stored in our qubit. So I spoke earlier of how we might want to utilize gates that change values in our computer to perform more complicated tasks, like addition, for example. So this is how we could do addition on a quantum computer. So here, I have two values I want to add, 0, 0. I have two values I want to add. So these could take on the values of 0, 0, 0, 1, 1, 0, 1, 1. And if I was to add these, so if I was to add 2 zeros, I get 0. If I was to add 0 and 1, I get 1. If I was to add 1 and 0, I get 1. And if I was to add 1, 1, I get 1, 0, because this is binary addition. When I add 1, 1, I get 1, 0. So this is how we can implement something like that in a quantum circuit. So here, okay, so like explaining this would be a bit difficult, but we have a 3-qubit gate here, and we have 2-qubit gates, and one of them is for the carry, and one of them is for the sum. So here we have the carry, and here we have the sum. So these are the gates that we use to implement that, and we can perform addition. There's also a full adder, so I'm not really going to explain this. Still the same concept. So here I'm adding 3 bits instead of just 2. Okay. I'm going to move on to variational quantum algorithms. So I don't know if there are any questions at this point in time. Okay, perfect. I'll proceed. So moving on to variational quantum algorithms. So currently, I used the word NISQ earlier. So this is what NISQ stands for, noisy intermediate scale quantum. So these NISQ devices, they have a limited number of qubits. We've not incorporated error correction. Our qubits, when we're performing computation with our qubits, over time, the qubits become more unreliable. And even our gates aren't like aren't overly reliable. We might want to do something. Let's say like in a classical sense, we might want to perform the NOT operator. That's change 0 to 1. And when we apply the gate in a quantum setting, at the end, instead of it becoming 1, it's still 0. So that's where we're currently at in the NISQ era. So we have a limited number of qubits. Our qubits aren't reliable, our gates aren't reliable. But we still want to create algorithms that are useful to us. So we need algorithms that are resilient to noise and aren't too large. So that's where variational quantum algorithms come into play. So we're utilizing both a classical computer and a quantum computer. So the quantum computer handled some parts of the algorithm, and the classical computer handled some other parts. And hopefully we can overcome the challenges we have in the NISQ era. So we can use variational quantum algorithms for problems in chemistry. I've already spoken about a couple of things we might want to do, like calculating molecular energies. So in using variational quantum algorithms for chemistry, we have some problem that will map onto our quantum circuits, and we might be interested in finding the ground states or simulating molecular properties. So this is useful for drug design, material design, and stuff like that. So also for optimization problems, similarly, we could have combinatorial optimization problems, and I'm going to speak a bit more on this later. So examples include, let's say, the traveling salesman problem. So this is a common problem in computer science, and it's a situation whereby you have a salesman that wants to travel, visiting various cities to, let's say, sell a product, and he wants to visit them just once and end back where he started, traveling the shortest distance possible. So this is something we could utilize, we could recreate as a combinatorial optimization problem, where we have the different routes that the traveling salesman could travel, and we're trying to find the most efficient route. So we could use this for logistics planning, supply chain management, stuff like that. Oh, sorry, I've left the slideshow. My apologies. I forgot about that. Okay, so even for machine learning, we have quantum algorithms, such as quantum support vector machines, quantum general adversarial networks, and these will utilize quantum properties for machine learning tasks like classification, pattern recognition, pattern recognition. So with our quantum circuit, we want to create more elaborate feature maps or kernels that will provide some advantage when dealing with complex data sets. So this is all I've been trying to talk about. So this is the structure of the variational algorithms. So they combine a parameterized quantum circuit. So parameterized, so like in maths, when we have like parametric equations, we use theta. So something similar here. We just have some value in our quantum circuits that we've parameterized, and we can change by providing different parameters. And then we have the classical side of our algorithm, which is an optimization loop that will try to find better parameters for our circuits. So the quantum circuit, it's also called an ansatz. So as I've said, it has tunable parameters. And when we run our quantum circuits, we'll measure and retrieve some values, and then we'll pass that on to the classical optimizer. And the classical optimizer will work with a cost function to find the best, to find better parameters. So it's like an iterative process. The quantum circuit to run, measure, provide values, pass on to the classical optimizer. The classical optimizer will compute some cost function and find better parameters and pass it back to the quantum circuit. And the process will keep repeating itself until we've retrieved some desired solution. So this is just like what the process looks like. We have our quantum computer, we run our circuits, we'll measure the values, we'll pass on to our cost function, and depending on what we get, our classical optimizer will provide new parameters, which is what we'll utilize in our quantum circuit once more. And we'll repeat the process until we obtain our desired results. So when working with our ansatz, so when working with the ansatz in our quantum circuits, the thing is that we want to explore. So as I said earlier, we have we have the values stored in our qubits in the form of vectors. So these are our quantum states. So we want our ansatz to be able to explore various states, but the thing is that there has to be some like technique in choosing or designing our ansatz such that we don't want the landscape or the different possible states that the ansatz can explore to be too large, but want it to be large enough to contain our desired solution. We also want it to be simple enough to run our quantum circuit because although they can handle errors, we don't want too much errors. So if you're utilizing too many gates, your circuit is running for too long, that can introduce too much errors, which we don't want. So when designing our ansatz, we have to be careful in terms of the number of qubits we use. We want to keep this to a minimum. The number of operators or quantum gates we're using, also want to keep this to a minimum. Also the initial parameters that we're using for our ansatz, because if we choose good initial parameters, we might be closer to our results, and that will be better for the entire like loop or process. So we also want to be careful type of operators because multi-qubit operators are more costly than single qubit operators. Okay, so we also have our classical optimizers. So they can be gradient-based or gradient-free optimizers. And the gradients based optimizers are sensitive to noise. So gradient-free optimizers are more common for these noisy devices. So this is an example. This is still like what I've been speaking about. Sorry, I don't know if someone's okay.
Yeah,
Someone's asking a
the
question.
concept of noise you mean in this direction. What do you actually refer to a noise? Excuse me, what I mean is this. In mathematics, we have classical problems that generally are seen as deterministic. You can really interpret what their solution could be. But we could have stochastic problems which have noise added to the deterministic states. In that case, a noise can be an interference from outside with multiple that affects the state of the system. So we have generally for that system what we call the deterministic and the stochastic part, which is the noise part. So in this case, I mean, I want to picture the kind of noise that you mean if it relates exactly to what Matt is saying, or there are other concepts or distribution of time. Thank you.
Okay. So thank you for that question. So in the classical deterministic systems, you are trying to say, let's say I start off with some inputs. Let's say I start with some inputs, 0, for example, and I apply an operator, such like a NOT gate. I'm going to end up with 1. So I'm certain that if my input is 0 and I apply that deterministic operator, I'm going to end up with 1 at the end. We might also want to create stochastic systems such that, let's say my input is 0 and I pass it through my computer or my mathematical function. And at the end, there's some probability I end up with 0 or 1. So because of superposition, our quantum systems already have that stochastic property that you're referring to, which is not the noise I'm talking about here. So the noise I'm referring to here is the noise I'm referring to here is such that let's say I had my qubits in the state 0. So I have 0 stored in my qubit. And I apply an operator that was to create that stochastic nature, or that was introduce those stochastic properties such that when I check my results at the end, there is some probability I get 0, there's some probability I get 1. But because of noise, for example, I could end up in a situation whereby every time I check, I'll just see 0. So although I applied an operator that I wanted an equal probability of getting 0 and 1 at the end, because of noise, I'll always end up getting 0. Or okay, not always end up getting 0 necessarily, but maybe instead of an equal probability, when I check, I might get 0 9 times out of 10. So it's not really following the distribution that I had in mind. That's what I'm referring to by noise. Okay. Okay, and even to just take it back to physics. So in physics, when we're dealing with isolated systems, the total energy, we know the total energy within that system. But when it interacts with its environment, or we have noise coming externally, we can have like a loss of energy. So I'm talking about something that I'm talking of, like loss of information or loss of energy along those lines. So it's something external, like affecting the setup I initially intended. So
Okay, thank you. I think Dr. Dozie asked a question.
okay, great. Sure, Dr. Odozi. I don't know if you're muted. I can't hear anything.
You can speak here. Okay, you can unmute. Okay, speak here. Okay, speak.
Okay, please, you talked about variational algorithms. Can you combine algorithms in one quantum computer? Or is it different algorithms for each field? Let's say chemistry, drug design, you have the algorithm. For computer, you have can you combine these algorithms in one quantum computer so that I can do any of that?
Okay, yes. So there are different types of quantum computers. Okay, let me just, okay, so like to answer your question like plainly, yes. So a quantum computer will most likely be a universal system that we can use to perform any algorithm that we're interested in. So we can use one quantum computer for chemistry, optimization, machine learning, or any other algorithm that we might be interested in. So what will differentiate, or what differentiates these different algorithms are the gates that we apply in our circuit. So as I'm speaking of variational quantum algorithms now, I'm going to actually show how a few like algorithms work. So we'll see a bit about how the circuits and all that are designed to accomplish a specific task. So we can use one quantum computer to implement different algorithms. I don't know if that answers the question.
Yes, thank you.
Okay, perfect, great. So move on. Okay, so this is everything that I've still been describing. So here we have our quantum circuits, or the ansatz. We could be trying to use it for some machine learning problem, for example. And this is the landscape of our cost function, where we're interested in getting the lowest possible energy value. So this is the classical optimizer that will help us traverse the energy landscape. So it's keep providing parameters that will update to traverse this landscape until we get to the minimum point. So this is just a couple of gates that we could use in our quantum circuits. So these are single qubit gates, and they are parameterized. So we have a parameter theta here, and we can vary something. So these are the parameters that we're going to be updating with our classical optimizer. And we also have 2 qubit gates. Okay, so I'm moving on to one possible variational quantum algorithm. So this is the variational quantum eigensolver. It's quite common for chemistry applications where sorry, it's quite common for chemistry, material science, and stuff like that, where we're interested in the ground state energy of some quantum system. So as I've said, the ground state is the lowest possible energy state. And unless external energy is applied, a system will always tend to settle in this ground state. So the ground state, okay, so I'm going to speak on Hamiltonian soon, but I'm still going to use the word here. So the ground state energy corresponds to the lowest eigenvalue of the Hamiltonian that we've represented using our quantum system. Okay, so I'm about to fully go into the Hamiltonian soon. But before I do that, I'll start off by explaining what an observable is. So an observable is some measurable physical quantity that we might want to read from a quantum system, such as the energy, the position, the momentum, stuff like that. And these are represented with Hermitian operators. So these are represented with Hermitian operators. So when measurement is made, so I have a quantum system and I measure it. So I've read out some values. When I perform that measurement, it was in superposition, but it's going to collapse to a specific state. So it's going to collapse to either 0 or 1. And 0 or 1, those vectors, they are eigenstates of the operator that was applied. The operator, okay, the observables operator. Okay, I guess I didn't properly, the Hermitian operator, that's what I'm referring to here. So when we perform measurements, we're going to collapse into one of different possible states, such as the 0 state or the 1 state, or if I had a multi-qubit system, 0, 0, 1, 0. So those are different possible eigenstates of some operator. And this operator is our observable. It's a Hermitian operator. So these eigenstates, they also have a corresponding eigenvalue. And the eigenvalue for that eigenstate, is the value that we've gotten or retrieved for that observable. So in the case of energy, I might have a 2-state system of 0 and 1. And let's say the 0 state had an eigenvalue of 1, and the 1 state had an eigenvalue of -1. So in such a scenario, if I was to measure my system and it collapsed to the 1 state, the value I get in that case is -1 as my energy value. So because we have our quantum states in superposition, so in the case I just gave about, let's say, 2-state system with 0 and 1, and I want to calculate the energy. So if it's in superposition, I'll have to perform measurements multiple times and get the average. So that's the expectation value. So let's say I was to get 1 8 out of 10 times. And okay, so that's my eigenvalue. So let's say I was to get 1 8 out of 10 times, and I was to get -1 2 out of 10 tries. I'll multiply 0.8, or let me see if I can annotate. So first of all, I spoke about sorry, I'm not a mathematician. I can't really remember the mathematical notations. So let's say I had some operator. So this is my Hermitian operator, my observable. And I had a quantum state. If I was to apply my operator to that state, I can get some eigenvalue. I can get some eigenvalue multiplied by that, I can get some eigenvalue, which is scalar value multiplied by that state. So here my Hermitian operator is a matrix, and the eigenvalue I have here is a scalar value. So this eigenvalue, let's say I had 1. So for the state 0, let's say I had an eigenvalue of 1. And for the state 1, let's say I had an eigenvalue of -1. When I perform repeated measurements and I'm to calculate the expectation value, if the probability of me getting 1 is 0.8, I'll multiply 0.8 with 1. And then I'll add this. Okay, so I've run out of space. I'll just write at the other end. I know this is not proper, but I'll have 0.2 at the other end. So this is how I'll calculate the expectation value. Or you know what? So okay, so I have the probability multiplied by the eigenvalue, and this is what I'll use to calculate expectation value. So this is the averaged outcome. Okay, so I'll move on. So this is an example. Sorry, did I miss something? Yes, okay, so this is where I'm at. So the Hamiltonian is an observable, and it's the observable that we use to get the total energy of a system. So it includes the kinetic and the potential energy. So I have some quantum system, and I want to calculate the total energy, which includes the kinetic and potential energies. I'll use the Hamiltonian. So that's the operator I'll use to extract this energy information from my quantum states. So the eigenvalues are the different possible energy levels, and the eigenstates are the quantum states that the quantum states that's the eigenstates are the different quantum states that have a definite energy level. So as I've said, the Hamiltonian is a Hermitian operator because it's an observable. So what I mean by Hermitian here is that this operator is its own inverse. So if I was to apply it twice in a row, that's like applying the identity. It's like doing nothing. And this is because we want the eigenvalues to be real values, because we want an energy value of, let's say, -1. We want real values for our eigenvalues. That's why we have Hermitian operators. as our observables. Okay, so why I was talking about the Hamiltonian and observables is because we have a quantum circuit and we want to use it for some problem. And this problem could be calculating the lowest possible energy. So in that case, the Hamiltonian is some function, some cost function for which I'm trying to find the lowest possible energy. So this is like this is a direct relation because what I'm trying to find is the lowest possible energy, and the Hamiltonian is the operator that I use to calculate the energy of the system. I just need to set up my cost function with my Hamiltonian, and when I get the lowest possible value, that's the lowest possible energy. Okay, so I'm almost out of time. So I'm going to speed it up. So this is an example. This is an operator. So this operator could be the Hamiltonian for a two-state spin system. And the lowest possible energy in this case is -1. And the state that has this energy is the one state. So we also have polymatrices. So I showed the Z polymatrix here, but we also have X, we have Y, and we can actually create any Hamiltonian by utilizing a linear combination of these poly operators. So here, one means I'm applying X to the first qubit and X here to the second, Y to the first qubit, Y to the second qubit. So this is a 2 qubits. This is a system with 2 qubits, and this is the Hamiltonian for that system. Okay, so I spoke about the fact that we have a parameterized quantum circuit. So as you can see, we have theta here for as the parameter to vary the state of our quantum circuit. And then we can utilize the Hamiltonian to read out the energy of that system. So the Hamiltonian provides us with the ground state energy. So whatever we find during this variational process, it will definitely be larger than the lowest energy. So either we get the lowest energy or any value we have, it will definitely be larger than the lowest energy. So we're just looking for the lowest possible value that we can get. So that's variational quantum eigensolver. We utilize that primarily for chemistry applications. We also have the quantum approximate optimization algorithm. So the VQ and QA, they are almost the same algorithm. If it's pretty much the same algorithm, really. It's just that VQE, we're using it to calculate the ground state energy for some system, whereas QAOA, we're trying to use it for some combinatorial optimization problem. So here we also have a cost Hamiltonian, and it's just some objective function that we're going to map to that cost Hamiltonian, and then we can find the ground state of this Hamiltonian. Sorry. Okay, so this is the function, and so we just have some relationship here, whereby this is our Hamiltonian and this is the const function. So we need to map our function to some cost Hamiltonian. So these are the different parts of the QAOA algorithm. So we have to initialize our quantum state at the start, and then we're going to implement a cost Hamiltonian. We also have a mixer Hamiltonian. So the initial states, we can obtain, we can create the initial states by just applying Hadamard gates. So This is a single qubit gate. We can apply it to all the qubits in our circuit. It creates this maximally superposed state, which is also the ground state of the mixer Hamiltonian. Okay, so because I've been speaking about Hamiltonians, and in our quantum circuits, we're applying unitary gates, we need some mapping from our Hamiltonian to those unitary gates that we apply. And this is what we use for that. So H here is the Hamiltonian. And this is any unitary gate that we could implement in our quantum circuits. So this is an example of the cos Hamiltonian after it's been mapped. So you can take a form like this. So we have some linear and quadratic terms here. And this is the coefficient of the linear term and the coefficient of the quadratic. And so this is what the mixer Hamiltonian is. It's all about. It just helps us explore the solution space and avoid getting stuck in local minima. So for the Hamiltonian, we might want to split it into several steps. And we're going to use the Trotter-Suzuki decomposition. I'm not going to speak much about this. So to actually split the Hamiltonian into this, we need it to, this is just Trotter-Suzuki decomposition. I'm not going to speak so much about that, but this is what we're trying to accomplish with it. And this is why, because we want to break down our Hamiltonian into separate steps and So this is the entire nature of the QAA algorithm. We have some cos Hamiltonian, we have the mixer Hamiltonian, and the cos Hamiltonian is the Hamiltonian whose ground state encodes the solution of the optimization problem. We prepare the initial states, then we construct the circuits applying the cost and mixer layers. So these are the cost and mixer layers. We apply it a couple of times, and then when we measure, we get some outputs. We pass it to our classical techniques to optimize, and we keep passing it up until we've optimized the parameters. And when the parameters have been optimized, at the end, the measurement results will provide us with the optimal, with the ground states or the solution to the optimization problem. Okay, so I don't know if there are any questions. This is the end.
Well, thank you so much, Mr. Kenneth. Personally, I quite enjoyed your presentation, but because of the short time, I might not be able to go too much into details. But I want you to do us a favor. One, we want you to give us, send us a slide so we can share with the students. Then we will love references. For example, in the aspect that has to do with these different forms of approximate optimization or algorithms that you have stated, we want more of the references to see it better than the summary that you have given now. For example, in the case of the Trotter estimate for the unitary case, I personally would love to see more of how that is applied or employed in application, because it looks more like some form of representation in mathematics. Though in mathematics we have unit representations, okay, but here the combination of this unitary representation here seems to be employed for a particular algorithm, which you call the Trotter algorithm or the Trotter estimate or something. So I think some of those references can also help us to get to understand it better and see more of the light. One thing I would love to know is in the unit representation, how did you eliminate the H bar? Because I'm seeing that the H bar is still there. in the denominator of the power. Yes. Yes. No, before
Here?
this piece.
Before here.
Yeah, before
Okay.
this, there was
Uh,
the H bar. When you, yes, yeah. How did you animate the H bar before you now employ it in the before it is shown to be applicable in the total Suzuki decomposition?
Oh, okay. So what I was representing here is that in our quantum circuits, that's where in our quantum circuits, I said that we have quantum gates, and these quantum gates are used to change the values of the value stored in our qubits. So these gates can be represented in the form of matrices, and these matrices, they have to be unitary matrices. And when I was speaking about the Hamiltonian, the Hamiltonian is a Hermitian operator, but it's not necessarily a unitary gate. So this is how we get unitary gates from the Hamiltonian. So these are the unitary gates that we utilize in our quantum circuits. So this actually comes from the Schrodinger equation. And this is how we like evolve the system with time. But yeah, it's meant to be unitary. It's unitary because we don't want like loss of energy. We don't want okay, yeah, I'll just say that we don't want loss of energy. Let me not just say too much. So for the Trotter-Suzuki decomposition I was speaking about, we could have like a Hamiltonian that is a combination of various like subsystems. So we've broken our Hamiltonian into smaller systems.
Question already. Yes, it.
Into
Continue.
smaller systems. And we want the evolution to be such that H1, it will evolve through H1, evolve through H2, evolve through H3, all the way to Hn. So it's supposed to utilize this evolution for H1, H2, H3, all the way to Hn. But if these operators don't commute, we can't rewrite this Hamiltonian as successive applications of this evolution. That is where the Trotter-Suzuki decomposition comes into play. So it creates this approximation. So even though the operators don't commute, we can utilize this approximation. And as you can see here, we're going to apply H1 all the way to Hn in succession. That's what the decomposition here provides us with. But here we just have the Hamiltonian, and we want to represent the Hamiltonian in the form of a unitary operator, which is going to be our matrix for the quantum gates.
Okay, thank you. The second thing is in your expression all through, I've not seen any form of tensor product being employed. And I know that in combining our operators, we generally use tensor products, but I don't know, maybe the way this is defined, but I was expecting that like the Hamiltonian has just splitted into n variables, so they are not necessarily end-to-end Hamiltonians that you can put together like the tensor product to do it. So is there any reason for this? Thank you.
Okay. Yes, thank you. Sorry. Okay. Yes. So the Hamiltonian we have here, I wanted to decompose it into subsystems of different Hamiltonians that I could apply in succession. So I have my quantum state, and it's supposed to evolve in time. So let me see, this is like at time 1, for example, and let me just use t. So let's say t1, and it's supposed to evolve to some later point in time, which is t2. So the entire evolution is going to be governed by H here, but I could break it down into these smaller changes up until Hn. Okay, so for my quantum state here, it could be, let's say, a 3-qubit system. It could be a 3-qubit system. So each qubit is going to be represented by some 2-dimensional vector. When I apply the tensor product, I can combine the states of these individual qubits into a much larger vector that represents the system as a whole instead of individually. So I can get an 8-dimensional vector here. So although I didn't necessarily use the term tensor product, when I was speaking about, let's say, a system with 3 qubits, I could use a tensor product for 1 here, 1 here, 1 here. And that's how I'll get the 8-dimensional vector. So the first entry here would be for the state 0, 0, 0, up until the final state. So there will be 8 entries. So here I'll have the amplitude that encodes the probability for 0, 0, 0, up until the final that encodes the probability for 1, 1, 1. So I didn't use tensor products because, okay, you also spoke about tensor product for the operators. So in that case, let's say I had Z1 applied to my first qubit. I can tensor that with Z2. So here I'll have a 2x2 matrix, and here I'll have a 2x2 matrix. And so 1 here means the first qubit, second qubit, and the third qubit. So my Hamiltonian could be Z1, Z2, Z3. So these are, or okay, well, okay, let me say the unitary operator that I want to apply in my circuit could be Z1 to the first qubit, Z2 to the second qubit, and Z3 to the third qubit. And these are all going to be 2x2 matrices. But when I use the tensor product, I'll combine it and it will create an 8x8 matrix, which I can apply now to the entire quantum states. So the tensor product, it just helps us like see the system more holistically as against seeing them in parts. While for the evolution I'm doing here, this is more like time evolutions. So H1 here could consist of Z1, Z2, Z3. I don't know if that makes sense.
Thank you. Yeah,
Yes.
I get it.
Yes.
Thank you so much.
Yes, so I could also have like H2 here. That could be X1 tensor X2 tensor X3. And that's how the evolution will go, encoding the entire evolution. Yeah, thank you. I don't know if there are any more questions.
Well, those online can type in the chat. I don't know if there are more people online that have questions. There's a question on the chat box.
Yes.
How do we represent the Hamiltonian for a single qubit?
Okay. So the Hamiltonian is what we use to calculate the energy of a system. So there's nothing like one single Hamiltonian that I can use to calculate the energy for every possible system. So every system has its own Hamiltonian. And I showed, sorry, I think I showed. Yeah, so I showed a Hamiltonian here, for example, that can be used for the spin of a single qubit. So like, let's say I have an electron and its spin. and I want to use my Hamiltonian in this case. So this is the operator for that system. So if I had a different system, I'll have a different Hamiltonian, which would be a different operator. But if it's going to be the Hamiltonian for a single qubit, it will have to be a 2x2 matrix or a 2x2 Hermitian operator. I don't know if that answers the question.
Yes, for me, I think I'm okay. What the person online can also respond. So I mentioned the issue of the materials. You didn't talk about that.
Yes, I'll share the slides. I'm a software developer actually, so I learn mostly from Qiskit because that's what I use to create the circuits. But I also utilize books like I can't remember the name. I'll definitely get references and provide them. I'll share them with you with the slides also.
Okay, thank you. I guess there's another question on the chat box.
In the Pauli matrix, how do you represent the Hamiltonian for a single qubit? In the Pauli matrix. Oh, okay. Wow. Well, okay. So first of all, I'm not use this. Sorry. Okay. So here I have a two-state system, and here I have a two-state system, and this is the Hamiltonian for that system. So I could also have a case because earlier when I spoke about the Hamiltonian, I said there is no single Hamiltonian that applies to a single qubit for all systems. But let's say my Hamiltonian for a single qubit, I could have some Hamiltonian in this form. For example, even just having Z, like this is actually the Hamiltonian I showed in the earlier slide, but I could have a Hamiltonian like this also. So representing my Hamiltonian here in the form of Pauli matrices. And I could also have weights here to show the impact of these gates, but okay, let me just introduce something like that. But yeah, so this could be my Hamiltonian for a single qubit. So there is no single Hamiltonian that applies to every single qubit quantum system. It just depends on what that system, like it depends on that system. Okay, so I don't know if there are any more questions or. Okay, so thank you, everyone. I'm really glad that I was able to be a part of the Qiskit Fall Fest, and I'm wishing you the best of luck through the entire workshop. So thank you.
Yes, thank you. Thank you so
Let
much.
me
All right, thank you, Mr. Kenneth. We really appreciate the talk today. So we look forward to having you another time. Thank you so much. So with that, we've come to the end of today's meeting, and then we'll see everyone tomorrow. So do by 10 a.m. Nigerian time. So see you all tomorrow.
Yeah, bye-bye. Thank you.
Thank you. Bye bye. Good night.
end the meeting.